Welcome to The Explainer. We're diving right in today because we've got something incredibly fascinating lined up for you. We are going to build a massive, complex enterprise network together, literally straight from the ground up. Whether you're actively studying network architecture right now, or you just kind of want to understand the invisible plumbing that keeps our modern digital world functioning, you are absolutely in the right place. We're going to break down the exact strategies used to connect everything from a simple desktop printer all the way up to global internet service providers.
So, think about this for a second. How exactly do you build an enterprise network that connects thousands of devices without it completely collapsing under its own weight? It's a critical question. To answer it, we really have to think like network architects. We can't just plug cables in and hope for the best, right? We have to build our topology piece by piece, starting with a single computer, scaling up to a massive campus, and finally wiring it all into the global internet. It's all about structured, deliberate design.
Here's our blueprint for today. 1. Switch ports, access versus trunk. 2. Designing and configuring VLANs. 3. Enterprise campus topology layers. 4. Inside EIGRP dynamic routing. And finally, 5. Mastering multi-protocol routing.
All right, let's kick things off with Section 1, switch ports, access versus trunk.
Let's start with the absolute foundation, which is just connecting a device to a switch. Before you can route traffic across the globe, you literally have to get data off a single machine successfully. Every port on your network switch is assigned a specific role, and your two main players here are access ports and trunk ports. You can think of access ports like private driveways for individual devices. They deal with untagged traffic, they belong to a single VLAN, and they connect directly to your PCs, printers, or IP phones. Trunk ports, on the other hand, those are the multi-lane highways. They pass data between switches, carrying traffic from multiple VLANs simultaneously, and they do this by using something called 802.1q tagging.
When you actually configure this on hardware, the traffic flow tells the whole story. The data frames coming from a connected PC are completely untagged. Honestly, the PC has no idea what a VLAN even is. But when that data hits a trunk port to travel to another switch, the hardware injects an 802.1q tag. It's basically a little label that says, hey, this data belongs to VLAN 10 or 20 or 30. And that tag is exactly what keeps all those different data streams organized as they travel across the network backbone.
Moving right along to Section 2, designing and configuring VLANs.
Okay, so our switches are wired up and communicating. But now we have a new headache. How do we segment different departments so they aren't all just shouting over each other on the exact same network? Well, the solution is virtual local area networks, or VLANs. They let us logically separate traffic even if it's running on the exact same physical hardware. But configuring them requires a very strict, logical flow. First, you define and create the VLANs on your switches. Second, you configure your access ports, assigning those end devices to their specific VLANs. Third, you open up those trunk highways we just talked about, explicitly allowing your VLANs to travel between the switches. And finally, and please don't skip this, step 4 is to verify your configuration to make sure everything is mapped correctly.
Planning this out beforehand is an absolute game changer. You really want to map out your broadcast domains before you ever touch a command line. For instance, you might dedicate VLAN 10 for sales, 20 for engineering, and 30 for guests, giving each one its own dedicated IP subnet. And why does this matter? Well, it comes down to security and performance. By separating them, you guarantee that a broadcast storm in the guest network doesn't suddenly take down your engineering team, and all that sensitive sales data remains completely isolated from unauthorized visitors. Let's jump into Section 3, Enterprise Campus Topology Layers.
All right, we've got our local network segments running perfectly. Now let's zoom out and look at the big picture. How do hundreds of these VLANs actually come together? In a massive campus hierarchy, you aren't just daisy-chaining switches together indefinitely, because honestly, that would be a total disaster. Instead, a robust topology solves traffic bottlenecks and single points of failure through a highly deliberate layered design. Traffic flows up from the local VLANs through very distinct tiers before it ever reaches the internet edge at the top.
So let's break these tiers down, because every layer has a very specific, crucial job. Down at the bottom, we have the access layer. This is where your users actually connect, and it aggregates their traffic, sending it up via bundled links, usually using LACP to combine cables for extra bandwidth. Next up is the distribution layer. Think of this as the smart middleman. It enforces routing policies and provides gateway redundancy using HSRP. That creates a standby backup router, so if one switch dies, another instantly takes over the gateway IP. Finally, sitting at the very top is the core layer. Now, the core doesn't care about policies. Its only job is to be a lightning-fast transport backbone,
rapidly switching massive amounts of data across the campus using a dynamic routing protocol like OSPF.
Which brings us nicely to Section 4, Inside EIGRP Dynamic Routing.
Now that our massive multi-layer campus is built, we hit a routing roadblock. Static, manual paths simply won't cut it in a dynamic network where links can drop at any second. We need a dynamic protocol to navigate this maze. To understand why enterprise networks choose specific protocols, let's compare EIGRP to an older protocol like RIP. We choose EIGRP, which is an advanced hybrid protocol, because modern networks demand fast convergence. When a link drops, EIGRP adapts instantly with event-driven updates. RIP, on the other hand, is notoriously slow and stubborn. It just sends updates every 30 seconds, regardless of what's happening, and it only calculates paths based on hop count. EIGRP is way smarter. It calculates the best path based on actual intelligent metrics, like bandwidth and delay. So it's not just looking for the shortest path, it's looking for the fastest path. At the absolute heart of EIGRP is a little something called the dual algorithm. That's the diffusing update algorithm. It's exactly what gives EIGRP its power. Dual ensures loop-free, completely reliable routing from end to end. It allows the network to dynamically adapt to changes, finding alternate paths almost instantly, and ensuring that your end users experience minimal downtime.
The way this actually works under the hood is just brilliant. First off, routers send out hello packets to discover their neighbors. Second, they share information to map out a complete topology table of the network. Third, they run those intelligent metric calculations for things like bandwidth and delay we talked about. Fourth, they select the absolute best path for the data. But step 5 is the real magic trick. They simultaneously calculate a backup route known as a feasible successor. Because they already have this backup path pre-calculated and just sitting in their back pocket, if the main link dies, the failover is practically instantaneous.
Finally, let's look at Section 5, Mastering Multi-Protocol Routing. So our campus is humming along perfectly with EIGRP, but real-world networks, they are almost never homogeneous. To connect to newly acquired branch offices or to route traffic out to the global internet, one protocol simply isn't enough. We have to speak multiple routing languages at the exact same time. In a massive integration, you might have OSPF acting as the internal backbone inside your core, while a legacy part of the campus is still running EIGRP. And out at the edge, communicating with external ISPs, you absolutely must use BGP. Specifically eBGP for external routing and IBGP to carry those external routes inside your own autonomous system. The true art of network architecture is making all these distinct protocols shake hands and share their maps seamlessly.
When you move routes between these totally different protocols, it's called route redistribution. And the golden rule here? Strict, unforgiving control. You cannot just blindly dump OSPF routes into EIGRP and vice versa. You have to plan this out carefully. You need to use route maps and tags to control exactly which paths are shared. You absolutely must apply filtering to prevent route bloat. If you do this wrong, you can easily create a catastrophic routing loop where data just circles endlessly until your entire network crashes. So document everything and monitor your paths constantly. Master this integration, and you're designing the difference between a fragile network and a totally bulletproof one.
Wow, we have covered some serious ground today. From the humble access port assigning a single VLAN, up through the redundant distribution layers, and all the way out to the edge routers managing global BGP tables. You've built the architectural foundation. But I want to leave you with a crucial thought for your next design project. Now that you've unlocked this architecture from end to end, consider how you would secure every single jump along this multi-protocol path. Because while an efficient network is amazing, a secure, resilient network is what truly defines a master architect. Keep exploring, keep designing, and we'll see you on the next explainer.